Hi, hello everyone. This is Nepal Reddy sir from ANR Academy. Today I am here with you to discuss about the concept of Leibniz theorem. And you people are familiar with Leibniz rule when the function has single variable. But today we are going to discuss Leibniz rule when the function has two variables. See here. The first result, here the integral function small f, that is with single variable t, and the second question, integral function f, it is two variables, having two variables x and t. First we will discuss the proof for first one, and then we go for second one, and after that we will discuss the problems based on first result, that is function with single variable, and then we will discuss one more question, that is based on a function it is with two variables. Let us discuss today. See the first result, differentiation of integral small f of t dt whose limits given pi of x to psi of x, and the result is f of upper limit into upper limit derivative minus f of lower limit into lower limit derivative. To prove this, I am going to select integration of small f of t dt, suppose that is capital F of t. Integration of small f, I am going to select capital F. Since the limits here pi to psi, applying lower limit pi, upper limit psi, then it become integral pi to psi f of t dt, that gives the result capital F of first upper limit substitution minus capital F of pi, then lower limit substitution. This is by definition of definite integrals. Now both the sides you have to apply differentiation. Apply differentiation with respect to x on both the sides. What happens? Observe. D by dx of integral pi to psi f of t dt. Now differentiation of this with respect to x. It is composite function. Internal function psi, outer function capital F. Second one also the same composite function. Internal function pi, outer function capital F. Differentiation of composite function, that is f dash of psi multiplied by psi dash. Next f dash of pi multiplied by pi dash it is. So that I can write d by dx of integral pi to psi f of t dt value. Clearly it become, you know that integration of small f is capital F and capital F derivative become small f. So it can be rewritten as small f of psi multiplied by psi dash minus, next this is small f of pi multiplied by pi dash, and hence this is RHS. This is the first Leibniz rule when the function has a single variable. Next, this one is second result, whenever the function has two variables x and t. See here, assume that capital F of x comma t, that is equal to integration of pi of x to psi of x f of x comma t dt. this portion I am going to select capital F of x comma t. That is, LHS part become d by dx of capital F of x comma t. That is clearly f dash of x comma t. Now I am going to use first principle. We know that f dash written as limit delta x tends to 0, capital F of x plus delta x comma t minus by using first principle f dash I am writing limit delta x tends to 0, capital F of x plus delta x comma t due to two variables minus f of x comma t whole divided by delta x it is. See here, capital F of x comma t, you have pi of x to psi of x, f of x comma t dt. Using this result, now I am going to substitute numerator part. This is clearly limit delta x tends to 0. It can be written as integral pi of x plus delta x to psi of x plus delta x. Since here the first variable you have x plus delta x, whenever first variable x, pi of x to psi of x. Next, integral function is small f. Here integral function small f of x plus delta x comma t dt. Next, minus sign, integral, this is capital F of x comma t. This one as it is I am going to write integral pi of x to psi of x, just small f of x comma t dt it is. Numerator over. Denominator part you have delta x, so that into 1 by delta x I am writing here. Now it can be rewritten as limit delta x tends to 0. Here integral function having limits from pi of x plus delta x to psi of x plus delta x. I am going to split these limits. You have lower limit pi of x plus delta x, and here I am writing up to pi of x, and then next I am going to split pi of x to psi of x, and after that psi of x to psi of x plus delta x. Just the limits from pi of x plus delta x to psi of x plus delta x changed as pi of x plus delta x to pi of x, pi of x to psi of x, and then psi of x to psi of x plus delta x. And next term you have to write as it is. Next term minus integral pi of x to psi of x, small f of x comma t dt it is, and here the integral function is f of x plus delta x comma t dt. Here f of x plus delta x comma t dt, f of x plus delta x comma t dt it is. Now from these two, the same limits you have pi of x to psi of x, but the difference in integral function. Also you have 1 by delta x. Here outside I am going to write 1 by delta x here. Right. These two terms with same limits but change in the integral function. In the next step I am going to write limit delta x tends to 0, 1 by delta x, and then first combination of these two limits pi to psi. Here you have f of x plus delta x comma t, here you have f of x comma t. So that you will get f of x plus delta x comma t minus f of x comma t integral dt, bracket close. Only these two terms. Next, remaining these two terms. First one you have pi of x plus delta x to pi of x. I am going to change the limits. When I change the limits, it becomes negative sign. Inside the bracket it is. I am going to continue here, minus integral pi of x to pi of x plus delta x. Just change in the limits gives negative sign. Clear? And here the function f of x plus delta x comma t dt. And another term you have this one, psi of x to psi of x plus delta x. This is psi of x to psi of x plus delta x, remaining f of x plus delta x comma t dt, bracket close. It is first this one, integral f of x plus delta x comma t minus f of x comma t divided by delta x, limit delta x tends to 0 dt. And next, minus sign. Here it is. I can say that limits of t. Here for both, t belongs to pi of x lower limit, pi of x plus delta x, this is upper limit. And for the second case, t belongs to lower limit psi of x, upper limit psi of x plus delta x. When you apply delta x tends to 0, t belongs to pi of x comma pi of x. Nothing but t changes to pi of x. This term I am going to write outside. F of delta x is 0. Why? Because you have limit delta x tends to 0. Applying delta x tends to 0, you will get f of x. As delta x tends to 0, t become t between pi of x comma pi of x, nothing but just pi of x. So in place of t, you have to write pi. Next, integral dt value t, and for which limits pi of x to pi of x plus delta x, and you have divided by delta x. Next term, it is of plus sign. psi of x to psi of x plus delta x. I am going to integrate this. Here again delta x tends to 0 means functional value become f of x comma delta x tends to 0 means only x you will get. Next t, when delta x tends to 0, psi of x comma psi of x. So t belongs to psi of x. Integral dt value, integral dt t limits psi of x to psi of x plus delta x divided by delta x. Right now it is integral dou by dou x of f of x comma t dt. Next minus, this is clearly f of x comma pi. By writing limits pi of x plus delta x and pi of x, you will get like first principle, it become pi of x plus delta x minus pi of x divided by delta x, and delta x approaching to 0 in this case, right? So that it become pi dash. Next f of x comma psi, again by substituting limits you will get first principle model, psi of x plus delta x minus psi of x divided by delta x, and delta x here approaching to 0, so that you will get psi dash. So remember that integral pi of x to psi of x f of x comma t dt, when the function is with two variables, then you have to remember first one. I am going to write this f of x comma upper limit derivative minus f of x comma lower limit derivative. In addition to this, you will get integration of partial differentiation of the function f with respect to x, partial differentiation of the smaller function f of x comma t, and whose integration you will get. So this is the proof of second one. And now let us discuss application problems. Here we have a question, limit x tends to 0, integral 0 to x square, sine of root t dt divided by x cube. Due to x approaching to 0, if you replace x with 0 in the denominator part becomes 0 cube 0. Next limits 0 to 0, integral 0 to 0, any function into dt, that gives the result again 0. Upper limit 0, lower limit 0 means you will get the result 0. So it is of the form 0 by 0. I am going to use L'Hopital's rule. L'Hopital rule says that you have to differentiate both numerator and denominator. I am going to differentiate this x cube derivative 3x square. Next here d by dx of integral 0 to x square sine of root t dt. Okay. Now, and you have to apply limit x tends to 0 for this. As x tending to 0, limit x tends to 0. Next you will get, just a minute. Now limit x tends to 0. Now for the numerator I am going to apply Leibniz rule. What Leibniz rule says? In place of t you have to replace upper limit root over x square, that is mod x, upper limit derivative 2x, next whole divided by 3 times of x square it is. Now x gets cancelled, 2 by 3 outside, limit x tends to 0, sine of mod x divided by x. Left hand limit, right hand limit I am going to calculate. As x tends to 0 minus, for 0 minus mod x become minus x. So minus sin x by x it is. As x tends to 0 plus, right hand limit, for positive values of x it is plus x. So that you will get sin x divided by x. Sin x by x as x tends to 0, it become 1, and as x tends to 0, it become minus 1. So that left limit not equal to right limit, so that limit does not exist in this case. Next, again here it is of 0 by 0 model. On differentiation, denominator part become 1, limit extending to 0. Now replace upper limit with t. It become cos cube of x and its derivative. Here the second term 0 by Leibniz rule, first rule, when the function has single variable. Lower limit 0, so that function with lower limit substitution and lower limit derivative you have, so it becomes 0. Now it is limit x tends to 0, cos cube x, that's all. As x tends to 0, it is cos 0 whole cube. Cos 0 value 1 cube, clearly 1. So here limit value exists, and in this case limit value does not exist. Why? Because root t you have here, that is root over x square. Root over x square is nothing but modulus x, remember, not x. Due to that reason, here sin of mod x you got in the numerator, and for negative values of x it is minus x, so minus of sin x by x, and for positive values of x it is sin x. So left hand limit not equal to right hand limit implies limit does not exist. Next, go for another question. Evaluate I equal to integral 0 to infinity tan inverse of ax minus tan inverse of x by x, and given that the condition a more than 0. This is clearly I of a. I am going to select this one as I in terms of a. Now differentiate with respect to a. Differentiate with respect to a. What happens? Observe. Two variables I am going to select, x and a. This is I dash of a d by dA, integral 0 to infinity tan inverse of ax minus tan inverse of x whole divided by x dx it is. So this is equal to here of integral 0 to infinity tan inverse of ax by x dx, and the second term becomes 0. Why? Because it is tan inverse of x by x, but the variable is different, that becomes 0. This is equal to, now integral 0 to infinity dou by dou a of tan inverse of ax. Here we are going to differentiate with respect to a, so that x is constant. Take outside. Now it is 1 divided by x, tan inverse of x derivative 1 by 1 plus x square. So that here 1 by 1 plus a square x square, internal function derivative due to with respect to a, you will get 1 by x. Sorry, differentiation it is, you will get x. X gets cancelled. So that here the value of I dash a, that become 1 by 1 plus a square x square. Actually this is Here you have to mention integral 0 to infinity symbol, right? Yes, integral 0 to infinity, forgot. And this is dx, okay. Now I dash of a, that is 1 by a tan inverse of ax, limits 0 to infinity. Therefore, the value of I dash of a become 1 by a. Applying limits, what we get? Tan inverse infinity pi by 2, tan inverse 0, 0. So that I dash of a we got pi by 2a. To get I of a, I am going to integrate on both the sides. Integral I dash of a dA, integral pi by 2a of dA. In the next step, integral I dash of a, nothing but I of a. Here pi by 2 constant, that is outside. Integral 1 by a dA you will get. Therefore, I of a become pi by 2 into log a plus constant. See the function. I am going to write a value 1. What happens? Observe. When you write a value 1, I of 1. When you put a value 1, only a1, tan inverse of x minus tan inverse of x become 0 in the numerator. So, the curve passing through the point 1 comma 0, remember. When it is passing through the point 1 comma 0, it is passing through 1 comma 0. So that if the value of a equal to 1, I of 1 clearly 0. I am going to use this, put a equal to 1. This is 0, pi by 2, log 1 c. Log 1 value 0. So that the value of c become 0. So that if you write c value 0, then what we get? I of a become pi by 2 into log a. So this is your answer. So this is about problems based on Leibniz rule when the function has two variables. Thank you so much.